We reviewed the overall workflow. Now, this is a hands-on session. We will go step by step. Please follow along and try each step yourself. Let's get started. First, let's download the R2GATE software. You can download it from the official website, R2GATE.com. R2GATE is free to download and use. Please note, it only works on Windows. It is not supported on Mac. Next, let's create your R2GATE account. Creating an account is free. When you sign up, choose your user type. Select either clinician or dental lab and continue. After installing R2GATE, you will see R2GATE, R2Ware, and the R2 Data folder on your desktop. Open the R2 Data folder and create a folder for your patient. Place the DICOM file and the STL file inside that folder. Now you are ready to begin. Let's launch R2GATE. On the left, you can see the patient list. This matches the folders inside your R2 Data folder. At the top center, you will see the DICOM files from the CBCT. In the middle, you will see the STL data. The last section is empty because no project has been created yet. To start a new project, click New Project. Enter the patient name. Then click Start R2GATE. The DICOM data is visible, but it may not look very clear. We will use the windowing function to adjust it based on Hounsfield units. First, we will use the mandible as our reference, since it is the densest bone. Drag the green line toward the densest bone area. In digital eye color, green represents the hardest bone, black represents air, red represents soft tissue or the weakest bone. Adjust the level so that the anterior mandible appears green. You can use the mouse wheel to make fine adjustments. Then adjust the width so that the soft tissue appears red. For the level tap, set the value according to the bone level, and for the width, set the value according to the soft tissue. If you are using only one CBCT machine, you can save these settings and reuse them whenever needed. Next, we will convert the CBCT into STL and define the matching area for the intraoral scan. Drag the green bar to position the area you want to convert. The yellow region shows the area that will be converted. You can adjust this range to include what you need and exclude what you do not need. Then click the Convert to STL icon. The green area indicates the region that will be converted. You can adjust this area using the keyboard. Press S to move it downward, press W to move it upward. You can also tilt the area using Q and E keys. From the preset options, select Teeth to isolate only the tooth area from the CBCT data. Then, click the Apply icon. The gray area represents the region converted from DICOM to STL. You can adjust the slider at the top to clearly visualize only the STL data. In the molar region, you may notice metal scattering caused by existing prosthetics. Avoid these areas when proceeding. Click the main STL icon to import the intraoral scan data. Since this is a mandibular case, select Lower. You will merge the data using 3 points. Click on corresponding areas in both datasets. Key point. The first point should be placed near the center, as it becomes the rotational reference during the fine alignment step. Then, select 3 clean areas, preferably on natural teeth, by right-clicking. If only the anterior region has clear features, use only the anterior area for point selection. If you need to undo a point, click the mouse wheel. Now, let's click the menu and move on to the next step. There are several steps in this workflow, but we will not use all of them today. In this session, we will focus on steps 1, 2, 6, 7, 8, and 9. Step 2 is the precise matching step, where you can fine-tune the alignment after the automatic matching process. C stands for center, R stands for right, and L stands for left. When adjusting these points, it is best to place them on the natural teeth whenever possible. You can then proceed with precise STL matching while reviewing the frontal, sagittal, and axial views. At the bottom, the 3 views are displayed separately, and you can choose from 3 different movement intensity levels. I recommend adjusting in the order of View 1, then View 2, and finally View 3. Because this is a 3D alignment process, you should check it from multiple angles as you go. After completing the larger movements, switch to intensity level 1 for finer adjustment. You can click the direction you want to move using your mouse or use the W, A, S, D, Q, and E keys on your keyboard. Once you have completed the adjustment, the next step is to carefully verify the alignment. You can do this either by dragging with your mouse or by using your keyboard. If your mouse pointer is in the upper area of the screen, you can move the view and check the accuracy of the matching. After completing the precise matching, make sure to review the C, R, and L icons one by one from different angles to confirm the accuracy. Careful verification at this stage helps prevent surgical errors and ensures a more precise outcome. In Step 6, you can perform the diagnostic wax-up. Since this is an immediate loading case, the teeth are still present in the intraoral scan data. So in this step, we will perform a virtual extraction. There are two extraction methods available. The first method uses a predefined shape to remove the tooth virtually. You can adjust the size and position of the shape to simulate the extraction. This can be particularly useful when extracting multiple teeth at once rather than working on a single tooth. The second method allows you to select the region of the tooth you want to extract. Once selected, the area will be highlighted in purple, and you can refine the selection by adjusting the control points. You may use whichever method you prefer. After completing the virtual extraction, make sure to save the result so the extracted condition is properly applied. When you select the corresponding tooth number, the tooth library will appear. You can adjust the position using the mouse or the keyboard. The center point allows free movement. The bars control translation. The arrows control rotation. The corner points control scaling. When arranging the crowns, do not check them from only one view. Since this is a 3D process, you should verify the position from multiple angles. You can also load the opposing data to evaluate the occlusal relationship. After checking the occlusion, I made some minor position adjustments. Once the arrangement is complete, make sure to save the diagnostic wax-up. Since this is a mandibular case, we need to trace the mandibular nerve. In the first view, drag the green bar downward until the mental foramen becomes visible in the second view. Next, adjust the green control points so the nerve can be clearly identified in the third view. Move each point as needed to follow the nerve pathway. Click the lock icon to fix the position, and then begin tracing along the nerve. Right-click along the nerve pathway to place points. When you reach the end, double right-click to complete the tracing. In the fourth view, you can move the tracing and adjust the size of the marked area. If the CBCT image appears slightly blurred or unclear due to movement or image quality, it is safer to draw the nerve slightly larger to help ensure a safe margin. After completing the nerve tracing, you can verify the traced nerve again in Step 8 while placing the implants. In Step 8, you will select the implant system and begin placing the implants in the planned positions. In the implant menu, you can select different components such as scan abutments, healing abutments, tie bases, and stock abutments. Extracting the scan abutment is very useful because it allows you to design the custom abutment before surgery. You can export the scan body data and import it into exocad or 3Shape to proceed with prosthetic design. In the implant list, you can choose from various implant diameters and lengths, and also select between normal thread, deep thread, and core-type implants, depending on your treatment plan. In the abutment menu, you can select different components, such as scan healing abutments, tie bases, and stock abutments. In other cases, even if not in this case, you can select a scan healing abutment and preview the size in advance. This helps you determine which healing abutment size to use after surgery. There are multiple diameter and cuff height options available, so you can adjust them as needed and select the most appropriate configuration for your case. Tie-base components such as Zergen and stock abutments such as Easy Post can also be selected in the same way. Since multiple diameter, cuff height, and post height options are available, you can preview and determine the appropriate size in advance. In addition, you can export these components and proceed with crown design. Once the design is completed, you can fabricate a temporary prosthesis by either 3D printing or milling the restoration in advance. There are multi-unit abutments available for full arch cases, and the AXA abutment library is also included. Since the full range of abutment libraries is available, you can select and use the components that best fit your treatment plan. Now let's move on to designing the surgical guide stent. First, we need to set the path. The red arrow indicates the path direction, and it changes depending on the current viewing angle. The path should be set based on the surgical site. After setting the path, you can see that the direction of the red arrow has changed accordingly. After determining the path, the next step is to select the area for the blockout. Please select an area slightly larger than the region where the surgical guide stent will be fabricated. The unnecessary areas outside this region will be removed, and only the required area will remain. If the selected area appears in purple, that means it has been selected correctly. Next, we will block out this area. You can see that the proximal areas have been blocked out. Because this blockout process has been applied, the surgical guide stent should fit properly without additional internal adjustment after printing. Now, we will create space to allow the drill to pass through. Non-sleeve or metal sleeves are available in 3 different sizes. You can select and order the appropriate size based on your surgical plan and use it accordingly. In the previous session, I explained that there are normal type and bi-window type options for irrigation. Now, I will introduce what the open type is. As you can see in the video, the normal type requires access from the top in a vertical direction. However, the open type allows access from the side, which makes it easier to approach in situations where vertical access is limited. The narrow type is used for MegaGen mini implants. The regular type should be used when the implant diameter is less than 5.0 millimeters. In the case of Blue Diamond implants, the guided surgery kit does not include a wide drill. However, since a wide carrier is available, placement of wide-size implants is still possible. This is an important point. When placing wide-size implants, both the regular guide and the wide guide are required. If you'd like more details or have any questions related to this topic, please feel free to visit megagenhelp.com. You'll find a wide range of helpful information there. In this session, we will proceed using the bi-window type. The sleeve offset refers to the tolerance between the drill and the guide hole. By default, 50 microns of tolerance is already applied, so selecting 0 millimeters means the tolerance will be 50 microns. Now we will begin designing the surgical guide. To achieve stable retention, the surgical guide stent should include 2 to 3 teeth on each side of the surgical site. After drawing the boundary, you can select the points and adjust them as needed. Select base roofing to create the thickness of the surgical guide. The minimum thickness here is set to 3 millimeters. Next, we will create seating holes to check whether the surgical guide stent is properly seated on the teeth. The seating holes can be created in either a cube or round shape, depending on your preference. The method for adjusting the size and position is the same as before. When creating this hole, be careful not to make it too large, as it may weaken the stent and lead to fracture. Next, I will create a round-shaped hole. Please position this hole over the cusp area so that you can clearly check whether the guide is properly seated. Now, to complete the surgical guide stent design, click Build R2GATE. Here, the offset refers to the space between the tooth surface and the inner surface of the surgical guide stent. This value can be adjusted depending on the accuracy and performance of the 3D printer you are using. Typically, I set the offset to 100 microns, which works well in most cases. The surgical guide stent design is now complete. Next, click STL Export to save the file as an STL file. Then, we will import the STL file into the 3D printing software to prepare for printing. Now, let's review all the files exported from R2GATE. Here, you can see the scan abutment that we extracted earlier, as well as the surgical guide stent properly positioned on the teeth. Now, I will demonstrate how to position and print the completed surgical guide stent using the 3D printing software. In fact, this process is very simple. Choosing a 3D printer with an easy and efficient workflow is also an important factor to consider when setting up your digital workflow. First, select the resin material. There are different materials available depending on the manufacturer and application. In this case, I selected SG01, which is the surgical guide resin from Shining 3D. Next, drag and drop the completed surgical guide STL file into the software. Then, select the application type as Surgical Guide Stent. The software will automatically position the model and generate the supports. Once this step is completed, the file is ready for printing. The software will also display the estimated printing time and the amount of material required. Now, everything is prepared and we can start the printing process immediately. The supports have now been generated automatically, and the positioning is complete. Let me show you how the 3D printing process progresses. If you adjust the slider, you can see how the model is built layer by layer. As you can see, the printing process continues by stacking each layer sequentially until the final model is completed. The supports have been generated automatically in appropriate positions. However, if supports are placed in areas where they are not desired, they can be removed or manually added as needed. The areas highlighted in red indicate the locations where additional supports are recommended or required to ensure stable printing. If you would like to print multiple copies of the same file, you can simply duplicate the model within the software. Even if you create several copies, the printing time remains the same because the total print time is primarily determined by the height of the model, not the number of units placed on the platform. After duplicating the models, you can also automatically rearrange the layout on the build platform for optimal positioning before printing. Today, I walked you through the step-by-step process of planning in R2GATE, designing a surgical guide stent, and preparing it for 3D printing. However, simply watching the process is not enough to fully learn it. The best way to make it your own workflow is to practice it yourself. I look forward to seeing you again in the next course. Thank you.